contractors, subcontractors, or even architects collect on a daily basis on job sites, in addition to billing information models. So I would like to start off with an example. And my apologies, this is a slightly more academic presentation because the demo I'm about to show you is a research prototype. The idea that we have, well, let me explain the building first. This is a building where our School of Construction is actually housed in, where Taniel and I actually work together there. And the idea that we have here is to see if we can take a photograph of this building, which was actually constructed back in 2007, and see if we can automatically recognize that in the picture, you can actually see that the stone wall is already installed, or even the stone on the top, or even the window is already installed. So the idea that we have is for you to walk around this building very slowly and capture a lot of photographs. And what we can do is we put these pictures together and give you a 3D point cloud model of the job site at the moment that these photos are captured. So in this particular case, we're using a collection of about 34 images. The spatial resolution is about 1.5 megapixels. So you can imagine you're holding your cell phone, walking around this building and capturing photos, and we can generate a point cloud for you in 24 minutes. Not only we can give you the point cloud, but we can exactly tell you where you took the photo from. So in this case, you can see the camera frustum and the photograph being superimposed on it. There's no GPS or wireless in this case. Everything is based on the visual content of the image. Now the idea that we have is to see how we can take this representation and compare it with the building information model and automatically analyze progress deviations. So I'm going to quickly speak about a few challenges that has actually motivated this research. So the specific focus of our work is obviously on progress monitoring, and the issue that we have is a pile of daily construction reports. I'm sure all of you, when you walk into contractor trailers, this is the first thing that you see, a pile of daily construction reports that usually contractors or construction management companies have to have 1 or 2 people analyze these data and understand how much progress is being reported by different people. Not only the process is very time consuming, but our contractors are not really providing a lot of information to us. Here's an actual example of a daily construction report that's been provided to Turner Construction, the company that I used to work for. In this case, the drywall contractor was reporting to us that they've been performing framing without exactly telling us the location of the framing, the cost of the work that was placed, or the amount of physical progress. And lastly, the way we are visualizing information is obviously very challenging. In this case, we have a construction schedule consists of 2,500 activities. You can imagine how much time you have to spend on a 3-week look at the schedule revision time. Or even the state-of-the-art representation of progress is a discrete representation. Then you have the construction drawings on one side, the schedule on the other side, and there's no easy way to understand the level of progress. So the idea that we've had is to see how we can use existing information on the job site and not add any type of technology. There's a lot of research that's being done on laser scanner, barcode and RFID tags, or variable computers, but instead of looking to those type of technologies, our idea has been to look into existing information. By existing information, I mean application of building information models. At this conference, we've seen a lot of application of BIM for design, pre-construction, and also lifecycle analysis of the building. This is perhaps another type where it focuses on taking the BIM and using it during the construction as a baseline for progress monitoring. On the other side, we have 2 types of information. We either look into time-lapse photography as a technique, or we just look into application of random photos, the photographs that everybody takes on the job site. So let me quickly explain the concept. Imagine that we have a 4-dimensional model where the BIM is already connected to the schedule. We want to take that model, have it superimposed on the photograph that is collected on that particular project, and in this case we provide you with an augmented photo. Once you have the augmented photo, the idea that we have is to see if we can go through the construction schedule and automatically analyze progress deviations based on different activities. And lastly, what we're going to do is to give you one single representation of progress, whereby using a basic traffic light metaphor, you're trying to color code those elements that are ahead of time, ahead of the schedule in dark green, and the elements that are behind are color coded in red. So now when we started this topic, our focus was mainly application of time-lapse photography. But every time I was presenting it to different contractors, they were always asking me the same question: what is the cost of your technology? Now a time-lapse camera only costs about $8,000 to $10,000 per year to operate and maintain in the US. But still it was a concern. So I decided to change the concept and see if I can use their existing photographs. So here's an example of the type of photographs that are already available to a construction management company. Another example of Turner Construction. In this particular project, we were collecting about 250 photos on a daily basis. Not only we were collecting photos, we had contractors taking photos for us too. In this case, it was actually a combination of 2 projects in Champaign, Illinois, and 18 different bid packages. If you assume that you only have 1 team, and each team is only collecting between 10 to 20 photos every day, you can see there's about 400 to 500 photos that are collected. But actually using these photos is not that easy. We don't know how these photos have been captured from, where they've been captured from, the lighting condition, the occlusions that we have. Sometimes they're taken for safety analysis, like this one that I'm pointing to right now. Sometimes they're captured for productivity analysis, or sometimes just documenting the quality of the work. So the challenge that we have, or the specific approach that we want to do, is to see how we can take these unordered set of photos, which are totally randomly collected, and turn them into a 3D point cloud model of the job site. Obviously, the case that we are dealing with is having a lot of occlusions and obstacles because equipment and people are working on the job site, so they're moving and they can impact our analysis. So the system that we've made is named D4AR, stands for 4-dimensional augmented reality, has 4 parts. The first part takes the set of unordered photos and turns it into a 3D point cloud model. The second component of the work is creating and developing 4-dimensional point cloud. That means using the photographs that are collected over different days to be able to generate different point clouds and fully automatically superimpose these models over one another. The third step of the work is to superimpose BIM over the point cloud, where the BIM would show you the expected progress, the photo would show you the actual. And lastly, see if you can automatically analyze progress deviations. So I'm going to take it out of the presentation and show you a demo of the system. So here's an example of the same site that I was just showing you. This particular case is reconstructed using 160 photos. Spatial resolution of these photos, only 2 megapixels. So again, you can imagine you're holding your cell phone, walking around and capturing these photos. So let me walk into this scene. You can see the facade of the existing building. You can see the construction equipment reconstructed. These were static the moment we were taking the photos. You can see the basement under construction, or even the steel structure that is already up for a dining hall project. Now what I'm going to do is to show you how the field engineer was walking and capturing these photos. So the area that I'm actually pointing to right now is where the field engineer started taking the photos, and here's how that person was walking and capturing photos. So as you can see, this person is casually walking and taking a lot of photographs. We zoom out a little bit. Now if you notice the size of the camera frustum, this little thing is not changing. Here's the moment that it changes. That means you can zoom in, zoom out, and capture whatever information you're interested in. Now what I'm going to do is I'm going to take all of ourselves and put it into the same position and see the site from that angle. So if you jump there, again you can see a 3D representation of the site. You can see the facade, basement under construction, there's a tree in the back, an excavator. Everything happens to be in 3D. We can also superimpose the photograph that was used to collect it. So in this case you can see the 2D versus 3D. 2D versus 3D. Now again, at any given position, you can preserve your location, turn your head around, and be able to see the rest of the site in 3D. Now I'm going to actually come slightly slowly out of the camera to show you where the camera was located at. And again, this is a mobile camera, a still camera in the hand of some person walking around and capturing photos. There's no GPS or wireless. So let me go back to the camera. I'm going to walk you between some of these photos just to show you how these photos have been captured. So as you can see, there's a lot of overlap. At any given point, you can turn off the textured image, and you can see the 3D status of the site. Again, at any given position, you can turn around and see what's happening on the other side. All right, so this is the first component of the system, which is helping us to document the existing status of the progress. But as I mentioned, the idea is to automatically analyze progress. So we bring a building information model. The way we are actually doing this is using IFC Engine DLL. So we've been using TNO's DLL to parse our IFC file, which was actually generated in Autodesk Revit and back into our system. So in this case, we can click on any given element. You can manually have it color-coded, and at the very top part, you can query the geometrical information. Now again, if your case is, for example, for billing purposes, you can imagine cost being associated with this element and having the actual representation. So let me go back to the photo. I want to show you the site from that angle. So if you go back to the photo, you see that this particular element that I color-coded is missing. So let me go back to a 3D view so you can see the element. From the photo, this element is missing. So what we can do is we can give you a little bit of transparency. So now you'll be able to see a semi-transparent photo. Let's see if I can make it better. There you go. The point cloud, the 3D model, and the color-coded element. Now we've taken this scene, which we call a D4AR, again stands for four-dimensional augmented reality. We've come up with a new machine learning algorithm that works based on linear support vector machine concept and color codes elements automatically. So in this case, the elements that are on the schedule are automatically color coded in green. The elements that are behind the schedule, those are automatically color coded in red. So now I have a question for you. Some of these elements are not color coded. If you notice, some of them are staying in a gray color, same color I had in the beginning. Somebody make any guess why some of them are not analyzed when you have photos?
On the ground? On the ground?
On the ground. When you don't have visibility to certain elements, if you don't have photo of your elements, you won't be able to analyze anything for you. So as long as you provide enough photos that gives you enough visibility for different elements, we can make an assessment. So in our system, we have a technique for measuring confidence factor. In our measurement of automated progress, we can have colors assigned when we have a feeling that we're going to get accurate results. Okay? Any question on the demo so far? Okay. So again, I'm not going to get into any of the details, but I'm just going to quickly do an overview of the systems that I showed you so far. So the first part of our system uses a concept known as instruction for motion to see how you can take BIM, how you can take image and a schedule and automatically analyze and get a sparse representation of the site. The second system component of our system is the process of taking the 3D model and superimposing that on top of the point cloud. This process is semi-automated. That means the user has to select a set of viewpoints from the BIM model, set of viewpoints from the point cloud, and then we can automatically transform the model for you. The third component of the work adds more density to the point cloud. And the last component, in terms of the analysis, automatically analyze for physical progress, which we have that machine learning algorithm. And finally, we take all this information and we visualize it for you, which I just showed you another example of that. Okay. Let's move on to the next slide. We've been testing this technology for a lot of companies, and I'm going to show you the name of the people who are partnered with us. This is an example of NIST, where we're going to engage in this particular case in terms of just using the only component of our system that does the 3D reconstruction. So in this case, we have a steel structure. The demo that I showed you was a concrete structure. We've only used 24 images, spatial resolution of 3 megapixel, and within 19 minutes, we've been able to get 2.5 million points out of this. Let me show you where the photo was captured from. So as you can see, there's a tire crane over here, and the photo was actually captured from the top of it. I put the name of NIST here because there's a safety issue. The board told them about this issue, and they said apparently this was done in the state of Michigan, where this is okay to have somebody tied off to the tire crane and take a photo. In the other 49 states, you're not allowed. All right, so just a few other metrics to show you how accurately the system works. As I mentioned, the process of superimposing point clouds is fully automated. So we have a system based on iterative closest point plus a scale. Takes any given 2 point clouds, which are not too much deviated, and it can automatically superimpose those for you. So in C, you can see A and B superimpose on one another, or down here, E and F are automatically superimposed and generate G. In the case of BIM, so now if you notice here, D and H are changed. The process is semi-automated, so we ask the user to provide us with a set of points. Now, there's a few reasons for this. First, you're using the system for automated progress monitoring, so at any given day, we don't exactly know the level of progress, so we want to leave that to the user to decide how the model needs to be transposed. But the good news about this is that if you register the point cloud model with a BIM once in the project, because the point cloud and point clouds are automatically superimposed, the rest of the process becomes fully automated. Just to show you some numbers in terms of the accuracy, the numbers that we have in terms of superimposition is less than 1 millimeter accuracy. So this selection error totally depends on how the user is selecting the points. The numbers that you can have, the minimum number to solve this question is only 3 points. So if you provide 3 control points from the survey, we can have this done for you. But again, because the user may incorrectly select the points, in these cases you can see we've chosen 7 or 9 points to have this process done. Now in terms of the automated assessment of progress, again, we've done some scientific study on that. Just quickly showing you some numbers. Machine learning algorithm that we're using is giving us an accuracy of 87% for training purposes, and we've only tested it so far on 2 projects for fully automated assessment of progress. In these case studies, we've got somewhere around 82 to 90% accuracy, and obviously we have precision recall and true positive, false positive graphs. Now, when you think about construction, you don't want to provide information about progress back at element level. You want to provide that information back at activity level. So here's just an example of a 3-week look at the schedule. For 4 different activities, we've tried to assess the level of progress. So over here you see for these activities, we have the level of progress identified by our system. But again, as I mentioned to you, because our system works based on photographs, and you may not have enough photos, we also provide you with a number on visibility. That means how much you can trust our numbers and how much is our confidence in our measurement. Now, to visually show you how those results look like, this is that example that I showed you. And here's another one. In this case, you can see the 3D model superimposed on the point cloud. We had a better accuracy, we had more photos, and the photos were all captured from inside the basement area. So obviously it ended up giving us a better detection accuracy. Just quickly showing you some examples that our system failed. One case on the top where it's a false positive. If you notice in this part of the scene, you see a form. So this area is still under construction, but our system has color-coded that in green. That's because our model is not using appearance-based recognition. It's only based on physical occupancy of the scene. Here's another example. I would like to call it mispositive, but perhaps in the statistical terms it will be false negative. This area is poorly reconstructed, and the way we've trained our machine learning algorithm, it doesn't recognize that progress. So it ends up color-coding that instead. So having said that, basically this system does a few things for you. One, automatically generates 3D point cloud models. Second issue is that it generates 40 point cloud model for you. In terms of the D4AR model, and again, we've tested it for level of accuracy. The whole process is fully automated. The only part that you have to do is to superimpose a beam on the point cloud. We've tested it for different exterior and interior cases. I only showed you 2 examples. We can handle occlusion. Obviously, these photos are all captured from real construction sites. We can interactively color code. So if you're thinking about using this system for billing purposes or coordination meetings, you can color code elements. You can query any information about as-built or as-planned, as long as you have that as part of your BIM. And perhaps this is one of the few systems that renders BIM, photo, and point cloud together. In terms of automated assessment, we've tested it for different types of elements and material, mainly concrete and steel structures so far. And we can handle partial visibility and occlusion. Because if you think about photos, at best, for some of the cases, you may end up having 80% visibility to a given element. Now, the alternative to our technology would be laser scanner. We're just claiming that we're reporting competitive accuracies. We've not done a proper scientific study to see how accurate our system is. Obviously, we need to figure out what number of photographs would match up with any given laser scanner. But we can definitely tell you that our system is cheaper. If you think about the laser scanner, it costs between $100,000 to $400,000 for the device. Nowadays, it's a little bit cheaper. But again, the cost of a camera is only about, maybe here in France, about 100 or 200 euros. Now, it doesn't need expertise for operation. If you think about the laser scanner, you probably need 2 people to operate this machine on the job site. You need to provide power, and you need to be able to perform post-processing. In the case of image, you can just provide the camera to anybody on your job site, and they can take the photographs for you. It doesn't add any new tasks for project management. In the case of barcodes and RFID that I mentioned to you, oftentimes we ask our field engineers to use those technologies to add this progress monitoring. But in this case, again, you're just using existing information. And we can capture the dynamics of the work just because we have the images that actually show where our equipment has been located. Now, you may want to contrast our work to old photogrammetry techniques. Comparing to that, our system is fully automated, so given the frequency of monitoring, probably our system is a little bit more practical. By that, I would like to just acknowledge all the companies that are helping on this project. Mainly, first, I would like to start with my PhD advisors. Graduated about a year and a half ago. Feniaski Kalamor at Columbia University and Silvio Savaresi at Michigan. The funding of this work has come up from Institute of Critical Technology and Science at Virginia Tech, National Science Foundation, NIST. We've had the alternate construction supports on this project. We are using this system at World Trade Center right now for testing of automated 3D reconstruction and assessment of progress. Giken Sakuchi from Japan. And all these companies that have either helped us with data collection, testing, or they're currently implementing the system. And I would like to leave you with a 3D reconstruction of some of my students here. And thank you very much for your attention. Here's a link to my website, and you can follow us on Twitter or Facebook at ROMAC Lab. Thank you.